Okay, so this is the transportation example. Now, most transportation linear programs, we basically have an origin and a destination. Here, the origin is two plants. We have plants in Marietta, Georgia, and Minneapolis, and we're trying to send our products to these four distribution centers. Now, our plants have what we call capacity constraints. That's how much we can actually produce in these factories. Marietta is obviously a bigger one, so we can produce 1,200 units in Marietta and 800 in Minneapolis, and we need a certain amount of units in each of these distribution centers. So this is the demand in the distribution centers. Now, this is a completely deterministic problem. You know, we assume the demand is fixed, but I guess we could um, add some additional analytics to have different linear programs for different estimated demands. But here we're just assuming that demand is fixed. So what we have here is basically for each unit, our decision variables you see here, here's the actual program. We would be, for example, Marietta would be plant one, Minneapolis would be plant two, and then we'd have distribution centers one, two, three, and four. So X11 would be the amount we send from Marietta to Cleveland, X12 from Marietta to Baltimore, X13 Marietta to Chicago, etc., etc., and X21 Minneapolis to Cleveland. Now, each of these journeys has a cost per unit. Again, we're keeping this very simple. It doesn't depend on the number of units. And obviously, you know, Cleveland and Minneapolis are both in the Midwest, so it's less than, for example, between Cleveland and Marietta. So it would make sense to send more from Minneapolis to Cleveland than maybe from Marietta to Cleveland. But the idea is we need to balance the whole thing. So we're basically trying to minimize our cost with our capacity constraints and also the constraints that we need to send a certain amount to um, each of these distribution centers. So we have the basic spreadsheet here. Again, I've taken the book spreadsheet and removed a few things so we can do it ourselves. So what we want to do is we want to compare, when we do Solver, we want to compare these constraints with our actual total sent from the plant, which is going to be here. These 8 values are going to be our decision variables. So our total shipped is just the sum of all of these. And then we can drop that down. So say, for example, we ship 100 here and 100 here, then we have a total of 200. And then the amount going to the distribution centers, this time is going to be the columns. So for Cleveland, it's how much we send to Cleveland from Marietta plus how much we send from Minneapolis. So it's going to be and we're just going to go to the right. And the total cost is basically going to be all of these values multiplied by the associated costs. It's going to be some product So say, for example, we send one from Marietta to Cleveland. That should be 1260. And then we have one from Baltimore to Minneapolis, which is 1626. We get 2886. Okay, and that pretty much just sets it up. So now we have to run it on Microsoft Solver. Okay, so let's go to Data, Solver. So we want to minimize, click Min, and we want to minimize the total cost by changing all of these cells. You can't have negative quantities, so they're going to be greater or equal to 0. So the first thing we want is the capacity constraints, that we can't have less than our actual capacity. So we're going to add, and these values need to be less than or equal to these values. And then we have our distribution center constraints. So each of these demands needs to be equal to the required demands. So those are our two sets of constraints. And again, this is a linear program. Look up here, we don't have any quadratic terms. All our variables are numbers. So we're going to click OK. And again, let's just have the answer and sensitivity reports. So here, note that, again, as I said, it would make sense to go from Cleveland to Minneapolis because this is pretty cheap. Baltimore to Marietta, staying on the East Coast. Chicago to Minneapolis because they're close together, so it's much cheaper. Phoenix is like expensive from everywhere, so Phoenix just kind of draws in the excess capacity. Whatever's left kind of goes to Phoenix. It's going to be expensive whatever happens. Okay, and our total, this is our total cost. Let's just have a look at our answer report. Again, we get the summary of the variables, and we see here that all the constraints are binding. This was like pretty nicely done. It kind of all added up. We didn't have any excess capacity. And then we have some of the sensitivity analysis. Let's just have a look at the shadow price. So this would basically say, you know, for each initial additional demand, so say we wanted to increase demand in Cleveland, then we would have to, this would increase our objective by this much, demand in Baltimore by this much, demand in Chicago by this much, etc., etc. Sorry, just give me a second, a bit of a cough. Okay, and sorry, where was I? Okay, let's just do the reduced cost. The reduced cost. This is just the amount you see. We're going from Marietta to Baltimore, and it's basically costing us. Okay, and the reduced cost. The reduced cost is basically just the improvement we need in the objective function to add something to the model. So, say for example, we have Minneapolis to Cleveland in the model, but we don't have Marietta to Cleveland in the model. And that's because it's much cheaper. You know, there's it's 9.75 our cost from Minneapolis to Cleveland, and it's 12.6 from Marietta to Cleveland. So this is just saying that if we reduce the cost from Marietta to Cleveland by 3.19, then suddenly Marietta to Cleveland would be included in the model. So again, it's just a little bit of addition, like with the shadow price, it's just a little bit of additional analysis that we can do. Just thinking a little bit about, you know, if this cost increased or decreased, then would this route suddenly become feasible in the model? Kind of like a little bit like the what if analysis that we did last chapter.